So here we have another question on advanced mechanics. So we're told a projectile reaches a maximum height of 15 meters and has an x maximum, so a maximum distance traveled of 25 meters. We have to A, find the launch velocity, and B, find the launch angle. So first we're going to deal with the fact that the maximum height is 15 meters. So we have a formula in our mechanics topic. The maximum height is equal to the velocity in y squared over 19.8. This is often written as 19.6. This is often written as 2 times g in the denominator. Now we know the max height in this case is 15, so we can solve this to find the initial velocity in y. So this tells us initial velocity in y is equal to the square root of 19.6 times the height. So this will be the square root of 19.6 times 15. So if I put this into my calculator, square root 19.6 times 15, that is 17.1464. Dot, dot, dot. So we will say the initial velocity in y is equal to 17.15, 2 decimal places, meters per second. So now that we have our initial velocity in y, we can use a range of formulas in order to find the initial velocity in x. So one thing we're going to do is we're going to think about our accelerations. Acceleration in x is 0. Acceleration in y is minus 9.8. Now our velocities. Velocity in x is whatever the initial velocity is in x. Velocity in y is minus 9.8 times time plus the initial velocity in y, which we just calculated, is 17.15. So here, immediately we can use this Vy formula. And the way we're going to use this is we're going to say at the max height, we're going to be quite clever about this. At max height, we know the velocity in y is 0. And so this means the t value associated with v of y being equal to 0 will be 1/2 of the time of flight, because that's how long it will take us to get from the start to the very top. And because we're modeling this as a parabola, double that, you have the time of flight. So this gives us 0 is equal to minus 9.8t plus 17.15. We will add 9.8t to both sides. This gives us 9.8t is 17.15. Divide both sides by 9.8, and this will give us t is equal to 17.15 divided by 9.8, which is 1.75. Now this is the time taken to get from the start, so to get from the start to the max height. Now we need the time of flight, which is the time taken to get from the launch or the start right until the end. So this means our time of flight is 2 lots of the time we just calculated. This will be 2 times 1.75. This is 3.5 seconds. Now we know another formula. We used a formula up here, this h formula. This is a max height formula as a function of the initial velocity. We have another formula, which is the x max, how far the projectile travels, is equal to the initial velocity in x multiplied by the time of flight. So now we're going to use this in order to find the initial velocity in x. So this means u of x is equal to x max divided by the time of flight. So this gives us x max, we said, was 25 meters. This was given to us in the question over here. Time of flight is 3.5 seconds. So we should have what, 50 on 7. So 50 divided by 7 in our calculator is 7.1428. 7.1428 ... So therefore, the initial velocity in x is about 7.14, 2 decimal places, and that's meters per second. Now we're going to draw a vector diagram to demonstrate these two velocities. So u of x is 7.14, u of y we said was 17.15. So if we draw a nice big vector diagram here, we have u of x across this way is 7.14, and then u of y up this way we said was 17.15. And in order to find the launch velocity, we'll do the square root of the sum of squares. So to find the value in A, the launch velocity, which we'll call u, is the square root of ux squared plus uy squared. This is equal to the square root of 7.14 squared plus 17.15 squared. So square root 7.14 squared plus 17.15 squared. That gives me 18.57 ... and this means the initial velocity was 18.58 to 2 decimal places, and this is meters per second. So this is the answer to part A. Now, because we did all the hard work in the setup to find u of x and to find u of y, and because we've already drawn this diagram, we can see this is the launch angle. We can see the theta in the diagram we've drawn, and that means we can just use tan to find that angle. So we'll have tan of theta is opposite over adjacent, 17.15 over 7.14. So we'll do shift tan or arc tan of 17.15 divided by 7.14. This gives me 67.39. So theta is 67.39 ... So therefore, theta is equal to 67.40 degrees to 2 decimal places. And this is the answer to part B. This is the answer to the launch angle. So pretty much we did a whole heap of work at the beginning to set up this question. By setting the question up correctly, by finding the initial velocities, both component pieces of the initial velocities, one in x, one in y, setting up a good diagram demonstrating that, it was easy for us to find the initial velocity, and then actually the second part of the question followed directly from that. So this is a case where doing a good amount of setup work did multiple parts of the question for you pretty much. And this is very common.